this computer. All right, so we're back. Yeah, so like what Erin just said, we only have 3 more pages to go. And a lot of this, well, this first page is actually terminology. So it starts with some review, and then there's a number of terminology things that we want to be clear about. So the 2 parts of a solution are the solute and the solvent. So if you remember, and there we go. I think I have to turn this light off. And the solute, I don't know how to turn that light off. Maybe we'll just do it like that. The solute is what is being dissolved, and the solvent is doing the dissolving. So if you think of salt water, so like in the picture over here, the solute is the particles at the bottom. Misconception is the states of matter. The solute can be a solid, liquid, or gas, and the solvent can also be any state of matter. And you can have a mix of any 2 states of matter. So an aerosol can is actually a solution. It's a mixture of usually 2 different gases that are in there. Yeah. And again, the solvent is almost always the major component. There are occasionally an exception to that, and that is because if water is present, it is always called the solvent, and sometimes it's not the major part. All right, solubility is something we actually talk about in 223 in more detail. So solubility is how much dissolves, so how much solute dissolves. Everything has a maximum amount, and as we see down here, both pressure and temperature do affect solubility. There is not a mathematical formula for solubility. It is experimental, and this summer we'll look, it's actually based on equilibrium. So in 223, the whole term is about chemical equilibrium. These terms, saturated, unsaturated, and supersaturated. This is why I want to do lab this summer, because there's a lab we do in 222 that we weren't able to, which is to make alum crystals. And you start with an aluminum can, and it's a really fun chemical experiment. And then you let the crystals grow for a month, and you get these little crystals, and people will make them into necklaces and stuff. But we end up making a supersaturated. But saturated just means you have the maximum solute dissolved. So if you had, this is like focusing funny. Anyway, if you had, so the diagram, I always draw a diagram on the board, is if you had a solution and you added 1 more grain of salt, it would not dissolve. So if you add more, it does not dissolve. So it would just float to the bottom. So here, like when you have a precipitate, it means the solution was already saturated. Unsaturated means it's below the max. So if you add more, it will dissolve. I did an experiment. Gosh, I could make you guys do this. And I had no idea this was going to happen, but I did it with the kids class, and they had a certain amount of water, and they had to add salt and keep stirring it until no more dissolved. And there was definitely a maximum amount, and it wasn't actually that much because we were adding spoonfuls at a time. And then they did it with sugar, and we pretty much could add almost a whole bag of sugar to 1 cup of water because sugar and water just love each other. But anyway, saturated is the maximum amount. Unsaturated means you're below the max. So if you add more, it's going to dissolve. And supersaturated just means you're above the max. And so basically you trick the solution. Often this is done, the best example is like with tea. If it's hot tea, you can add a lot of sugar to it. And then if it cools down, slowly the sugar will stay in there, and so you can add actually more sugar. What happens if you add 1 grain, you'll pull out all the extra. And this is the lab that I would love to do this summer. So all the extra solute comes out. If when you were a kid, there was these kits that you could grow like castle or the rock castles and stuff. Those were super saturated solutions. So you would heat it up in the microwave, and then you would just put it in a bowl and let it sit. And over the next couple of days, you would see these formations happen. And so in lab, we make a super saturated solution and we let it sit for a couple of weeks and a crystal forms. All right, so everything has a saturation point. So this is just, I'm going to make up a number. If something, let's say its saturation point is 5 grams per 100 milliliters, then unsaturated would be anything less than 5 grams per 100 milliliters. So if you had only 2.5 grams, supersaturated would be anything more than that. Saturated would be just that 1 point. So saturated is just one specific point. This piece here, which is really small, we've talked about a lot, especially with the first midterm. This is that polar likes polar. So polar and polar mix, and non-polar and non-polar. And how that's important is with water. Water is polar, so things that are polar mix with water. So the question below it goes with this. The ones that are miscible. So the word miscible to a chemist means that you can mix the two things. So if they are both polar, then they will mix. If they are both non-polar, they will mix. So like C would definitely be yes, because it's non-polar and non-polar. So if you remember back, we've actually seen this with each of the midterms now, and it was a theme, and I mentioned it the very first video I made. It was something we work with a lot this term. When you see only carbons and hydrogens, it is non-polar, so non-polar and non-polar mix. B is nope, because water is polar, and then something that is non-polar doesn't mix with it. And this is why oil spills, so C8H18 is octane, and this is why oil spills are so devastating, because they don't mix with the water. But otters and birds, they have non-polar coating on their feathers and fur that actually waterproofs them. And so that non-polar means they don't feel the wetness. And so if you go to Alaska, you see these animals swimming in the water that's frigid, but they don't feel the temperature. And then when an oil spill happens and they get coated in the oil will dissolve this lipid coating on them, and they will get hypothermia. They'll get really cold because they can suddenly feel the water. Yeah. And so usually the other thing we do this term is we make soap, because soap is both polar and non-polar, so it mixes with both. A we would circle, because A is polar and polar, so they both hydrogen bond. So when you see NOF, NO and F, we're going to see polar. D is also nope, because this one has an OH and this one is carbon hydrogen. So that's something we've been working on the whole term, and it really goes with solutions because we're starting to mix things together. All right, I'll just keep going unless you guys have a question. All right, and the next one is just some terminology again, this page. These are all 3 types of mixtures, so they are mixtures, and the difference is the size of the solute. So the size of the solute particle. And there's a little picture next to it with really little words, and I'll have students memorize that. You don't really need to memorize it. A solution means the solute you cannot see. The solute is really itty bitty, teeny weeny, itsy bitsy. You can use whatever adjective you want. It's really tiny. You cannot see it. you cannot see, you cannot filter, because there is no filter that can filter out the solute in a solution because it's too small. And so it does not separate. And another thing with that is it looks the same throughout. So a great example is the room that we're all in, each of us individually, is actually the air is a solution. It's the same anywhere we go. Anywhere you take a sample of it, it's going to be similar. If you, the water, tap water is a solution. So wherever you drink tap water, it does taste different. So Aaron's in Missouri now, and he can tell you the tap water. And you might be on well water, actually, from what you've described where you live. And so if you're blessed to be on well water, you get lots of minerals from the area, from the groundwater and stuff. A colloid, the solute is small, tiny. And the best example of this is fog. That's like the #1 example, because we've all seen fog. And that's one of the things that's really cool in Oregon. If you ever go to the Oregon coast, you see colloids all the time. And what happens if you try to drive in fog is you can't, because your headlights get dispersed. So the solute disperses, because it's tiny, it disperses light. So in a solution, the solute is too small to make the light particles disperse, but in a colloid, the particles are just big enough that if you shine a light at a colloid, the light will go in every direction but straight ahead. And that, there was the guy who illustrated this was called Tyndall, so it's called the Tyndall Effect. But again, if you've ever tried to drive in a fog, it's, well, we say we're in a fog too in our heads sometimes. And this is why when you go to like the Redwoods, my favorite place, the Oregon coast, you can take amazing pictures in the morning because of the effect of the light on all the water vapor that's in the air and stuff. Another example of a colloid is actually milk, Jello. I did this with the kids, and we took lasers, and it's actually really hard to do, but you can't shoot a laser through milk or Jello because it disperses it. It makes it go, and that's because in Jello there's proteins called collagen that are too big. And another example of a colloid, well, actually, let's do a suspension. In a suspension, the solute is large, and it separates on standing. And the big examples here would be mud. So like right now, we just had a big storm this afternoon, which is really cool. So there's lots of mud puddles, and if you let them just sit and it stops raining, the mud does eventually settle. Another example is paint. So if you've decided, many people right now, because they've been home, decide to paint their house. And so they go and they get paint, or they have some in the garage from a year ago, and they open up the paint and they go, ooh, it's bad, because the solute and solvent separated. And so then you have to mix and mix and mix. When you get it at the store, they put it on a machine that shakes it and shakes it and shake it for like 10 minutes or something. And so they're mixing it together really well. Another example of a suspension is your blood. So if you took a sample of your blood and you let it sit for long enough, it would separate. The red blood cells are heavy enough and large enough that it would separate. And then you'd be left with a colloid, which is the plasma, which still has particles that are pretty large, and then you're left with the solution. So once you take the cells out, but our blood cells are large enough that they will separate with time, and that's how they can tell how much your percentage of red blood cells is. We put it in a centrifuge and settle it. And that's why I was saying, if by some miracle we can go on campus this summer, the labs we do this summer are really cool. And we use centrifuges which spin the stuff really fast and separates in 10 seconds rather than letting it sit for 20 minutes and waiting and waiting and waiting. All right. So we're good? I think in the homework there's some questions that we'll ask about these. All right. So we're going to look at the pressure and temperature effect. And then the last 2 pages is actually, there is some other new stuff on those pages too. So pressure, you guys actually know both of these effects. Pressure's mostly on a gas. So if the solute is a gas, as you increase the pressure, you're going to increase the solubility. And that is why the champagne is shown as a picture over here. It is, or soda, it's when you open the soda, it always pops off and you hear a fizz or a champagne bottle. And so they use pressure to push the CO2 into the soda or champagne. And then when you release it, and so it makes sense. As you increase the pressure, you're pushing the gas into the solution. And so it becomes more soluble. There is actually a gas law called Henry's law where they would show that. And so it would be a ratio, right? If they're directly related, that the pressure over the solubility, right, of A would be equal to the pressure of B over the solubility of B. And that would be assuming constant temperature, because temperature also affects solubility. You don't really need to know that law, but it is often traditionally taught with gas laws, because it works just like a gas law. And so he was the one who figured that out. For our purposes, you just need to know the basic idea. For temperature, it's interesting. Again, if the solute is the gas, if the solute is a gas, as you increase temperature, you actually decrease solubility. And this is why we like, in this country, we like our soda cold, is when you decrease the temperature, so you have the soda cold, or whatever the carbonated beverage is, more CO2 is in the beverage. And so when you drink it cold, you get that bubbling effect. And people in our culture in the United States like that fizzy, bubbly effect. If you go to most other countries, because they don't have the refrigeration that we have, they don't actually like their sodas cold. Although it is a, it shows you're wealthy if you can have it cold, because, right, you can get dry ice or whatever. This is also one of the problems with global warming. So as the temperature increase, we've decreased the solubility of oxygen in our water. And that means the fish die. So we have dead fish. So you can draw a dead fish. He's dead. Dead fish. Our fish are dead. So here in Oregon, the salmon often cannot make it all the way to their original breed where they were hatched. They want to go back there to lay their eggs, but the water temperature doesn't allow them to get back there because there's not enough oxygen. Now, of course, with this pandemic, there's some interesting things happening. So now this is one other thing, is if the solute is a solid, it is, as you increase temperature, I'm going to put a question mark, but usually you do increase the solubility. Whoops. So as you increase the temperature, and so think about what I was saying before with sugar in water. So a lot of people put a lot of sugar in their tea or coffee, and if it's hot, you can add more, a lot more dissolves. That was what I was saying. I did a lab with the kids, and they added salt to water, and then they did hot water, and they saw how many teaspoons of salt they could add. I could have you guys do that. It's still right in your lab for next week. Anyway, is there questions on any of these terms? It's just some of the basics of solutions. And then some of the things I was writing here in the middle are some of the properties of solutions. I think in the study set, oh, do I have the study set? I think there's some questions, and yeah, and maybe, yeah, just a few. All right, let's move on. So a review of units. So this is key. And again, you guys have a huge advantage because you can keep your notes. So I tried to organize it for you. So when for your next midterm, again, you'll have a limited amount of time. So just make a nice note card or a piece of paper where you organize your units. And if you sincerely do the homework and stuff, then you'll be fine with the test. So this is percentage. M per M means mass per mass. So this is grams of the solute over grams of the solution. And solution just means total. It is a percent, so you would multiply by 100. The funky X means mole fraction. And so percent, we do multiply by 100. For a fraction, we do not. And so it is similar, it's just with moles. So it's moles of the solute over the total moles. Or the moles, I'm going to here say total moles. You can say the moles of the solution also. And it will always be, I'll write it above, less than 1. Because it's just saying how much. We don't multiply by 100. All right, the next two, it's important that we don't mix them up. One is molality. And again, the only use I know of molality is it does allow us to predict freezing point and boiling point, which we'll do on the last page. And then molarity, this is the most common unit of all. We talked about it in 221. We're talking about it here in 222, and it is a central theme in 223. Every single thing we do is molarity. So molarity is moles per liter, which you hopefully know. But with this study set and worksheet and exam, if you label it like that, you'll lose a point because it's not fully labeled. So you never just say moles, you have to say moles solute. So moles of solute over liters of the solution. Molality is moles of solute. And it is over kilograms of just the solvent. So molality is very special because the denominator is not the total. So if you look at the other three, the denominator is the total grams, the total moles, the total volume. But on molality, molality is a unique one. All right, the point about density, we do some stuff with density. Yeah, down on this one. The density is always, has to be, it's obviously grams per milliliter. But the other part has to be the same thing above and below. So it'd be grams of the solution over milliliters of the solution. So you cannot have a density unit that has a mixed top and bottom. It could be grams of solute over milliliters of solute, but typically we're going to see it like this, where it's grams of the whole thing over the milliliters of the whole thing. All right, so that's a review of the units, and we're going to do problem solving, and these are a little bit more challenging than the ones we did the other day, because they have us making an assumption. And I picked the tough one to start with. The one we did the other day, and I'm just going to flip to it, you don't have to. I gave you the amounts of each, the solute and the solvent. And then here we did make an assumption. When you have a percentage, the assumption's really easy. You just assume the total is 100%. So the 28 was the NH3 and the rest is the solvent. So the two pieces add up to 100 grams. So percents are pretty easy. So the one here, that was on the first page. So the one we're doing today though, I give you a molality. And so we're going to start with an assumption. And so our assumption is that we have 0.454, excuse me, and molality means moles, and silver nitrate is AgNO3. Don't know if anybody remembers that. Silver nitrate's really actually a cool topic. Now the key with an assumption is you say and, you don't say slash. And we have 1 kilogram of H2O. So a reminder, if I do not tell you the solvent, you want to say it's water. But this is what molarity means, you're over 1 kilogram. All right, so that's our assumption. It's basically rewriting what the question, what the given is in the question. So that's our assumption. So what we're going to do now is calculate the percentage. So percent means we want the grams of the solute over the grams of the solution. So whenever you're doing the problem solving in this chapter, you want to always first state your formula, kind of like when we did gas laws, similar. And then we're going to now solve. So we don't know the grams of the solute, but we do know we have 0.454 moles of silver nitrate. And oh, look at that. We have a periodic table. We can change moles to grams. So that means we can change moles back to grams. So you guys know how to add up the silver, the nitrogen, the oxygens. You add them up. I already did it for us. So you would change your moles to grams. I'll leave it for you guys to do. And then on the bottom, this is the part that's interesting. Oh, we have to do this step. Dang it. Because on the bottom, we need the total mass. And what we know right now is we have 1,000 grams of water, but that's not the total. We also need the grams of the silver nitrate. So we have to figure out that number on top. So let me give you guys a moment to figure out how many grams of silver nitrate you have, or I will figure it out while you write your stuff down, because we're going to need this number anyway. All right. So so this is 169.9. So around 170. I think when I taught it in 221 for students who were with me there, I just always went to one decimal place with my periodic table. If you rounded to 170, that's not a big deal. Or if you want 169.91, it's also the same. And notice this time, because we're at moles, so the 169 we're going to be multiplying. So times 0.545. And so this is going to give us 77.1 gram of the silver nitrate. So that's my numerator. I need that number down here, the 77.1. So my total grams is 1,077.1 grams total. And then I would just divide and multiply by 100. And we get 7.16. All right, I have to make a quick comment about sig figs. Let's try and respect them. This problem's really simple. All the numbers gave us 3, so we just use 3. The periodic table usually gives 4, so it is whichever number gives you the least number of sig figs. So we're halfway done. There is one more piece with this question. I didn't give myself enough room. Was there questions with that? Does that make sense, the assumption? So with molality, this is the hardest thing students have had in the past. I think you guys have a huge advantage because you can go back and rewatch the videos, which part you want. I've been watching my son watch videos, and he does. So like rewatch the same part 10 times, and then he'll zip through the other parts because he's like, oh, I got that. So it also wanted us to find the mole fraction. So for mole fraction, I'll do it here. State your formula. So X is the moles of the solute over the moles of the solution. And the numerator we know. I'll move my arrow over here. We already know it's 0.54. So in our assumption, that allows that to be true. And in the denominator, I have the 0.454 moles. Sorry, I keep saying that wrong. And I have to add it to the water. So we know we have 1,000 grams of water because that was our assumption, that we have 1 kilogram. So we'll say we have 1,000 grams H2O, and we would just change that to moles. Now, I personally like to do it all in one setup, but you can break it into steps as long as I can follow your pieces. And water is somewhere around 18, like 0.016. And right. So our answer is up here, 0.00811. I'm going to assume that's right. Hooray. So just a quick reminder for all of you watching, please make sure you label everything fully. I did notice on the midterm, people were really conscientious of that. And with solutions, that is actually the key. The students who take the time, some of you've all been actually showing your work beautifully. Yeah, so don't just ever say moles. With this chapter, you have to say moles of what? Because there's always two components. There's a solute and a solvent. All right, if you guys don't have questions, we're gonna move on. All right, the next one tells us we have 83.5 grams of silver per metric ton. Metric ton is 1,000 kilograms. Again, you can always Google that, but that's what a metric ton means, which would be 2,200 pounds. Everyone pretty much, a ton now means a metric ton. We've pretty much worldwide moved into the metric system. All right, so we're gonna do something called ppm. So ppm means parts per million. And when we use ppms is when something is very, very, very small amounts, very diluted. So we have a very diluted solution. It is used when we're dealing with toxins. So you don't need a lot of a toxin to contaminate something. So like if you have mercury contamination, that's usually in parts per billion, ppb, or ppt, parts per trillion. Yeah, a lot of chemotherapeutic stuff. All right. So parts per million work the same as a percent, that it's the mass of your solute, but a percent is always, you think of it as a million. You can think of it as the same as this. So this would be over our grams of our solution. I'm going to show it to you this way first, times a million. So percent is times 1,000, parts per million, you would say times a million. There is another way they teach it, and that is, and I'll just put it underneath, it's done with things like toxins. They'll often say milligrams per kilogram, and then you don't multiply it by 1,000,000, because the difference between a milligram and a kilogram already factors in the that number, the million. All right, so up here what we would do is take our 83.5 grams of silver. We're not doing anything with moles, and we put it over our 1,000 kilograms, which we would have to change to grams. So 1,000 grams per kilogram. And then you'd be multiplying by the million. So this is the piece that's interesting on this one. Because it is so diluted, the solvent and the solution are interchangeable. The solute, I said that wrong, the solvent and the solution are interchangeable. Because it's there's so little solute, but basically we'll get 83.5 because the denominator is 1,000,000. So we would have 83.5 parts per million. Right. And then it wants us to change it to molality. So to do molality, state our formula from above: moles of solute over kilograms of solvent. So this is what I was just trying to say. It holds true for parts per million that the solution and solvent are interchangeable. So we know it's 1,000 kilograms. And we have 83.5, and we would just, it's just silver, so 107.9 grams per mole. Again, using our periodic table. I think you guys all know how to use that. So silver, reminder, is Ag, argentium, because the Incas, who were amazing, very enlightened people. And so that would be our setup. That would give us molality, and that should give us that answer there, 7.74 e to the -4. And the unit, you can either write it as M. A lot of students will write it as moles per kilogram because that makes more sense in their brain. So either way is fine. And if there's no questions.
Ooh, I actually have one.
Go ahead.
I was wondering, for the first part of the equation, when you have the 83.5 over 1,000, does the 1,000 have to be labeled?
Gram. It's, yeah, so that's, I did not, because with parts per million, it can be the solution or the solvent. And I didn't actually say what it was. I said per metric ton, but I didn't say, is that of the water or of the solution? So you are correct, Aaron, because I kept saying you need to label it. This is the one time that you can get away with it. So you could have said, you could have either said solution or you could have said water. Because it's so diluted, and that's also true with parts per billion, even more true. And actually, ppb is parts per billion, and if you want to make a note. Yeah, that's a really good question, and thank you for asking that. So I did mention that you want to always label the top and bottom, so you can say either solution or water on the bottom here. Like over here, technically this is just water, and this is the one time when you can interchange it. But parts per billion, you can either do it as grams per gram times 1,000,000,000, 10 to the 9th, or they often will say it's micrograms per kilogram. So like in medical fields, if they're dealing with a chemotherapeutic agent, they're usually extremely toxic. And we talk about our body in kilograms, and then the drug that they're giving in micrograms. So they'd say micrograms per kilogram of body mass. And so that's parts per billion, because there's a billion difference between those. And then there's some things that are so toxic now, man-made stuff, and it is truly parts per trillion. All right, other questions. And that was a really good question. Let's move.
Thank you.
To the last one is we're solving for molality and percentage. Oh, I mentioned this the other day. So this is a good typo I did, because you'll probably, W per W is the old way of saying it, where we said weight per weight. And you will still see that a lot, especially out in the real world. In chemistry class, we will say M per M, meaning mass per mass, or usually just like what I say here, percentage by mass. And so what we know is we have a 0.21 solution. And this one is not made up of water. It's made up of C7H8 and C6H6. So the toluene is the solute. And I know that because it says it's dissolved in the benzene. So the benzene is the solvent. So H2O does not show up in this problem. All right, and we get to do an assumption. So that's why I have these here, because we get to see how to make an assumption. So what we have is a 0.21 molar solution. So what I'm going to assume again is I have 0.21 moles of my solute, so the C7H8. And so again, you don't say a slash, you say that word and. And so instead of saying I have 1 kilogram, this is molarity, I have 1 liter, because it's a capital M. Now, back to the question that Aaron just asked, and that I kept trying to emphasize, you have to label that liter, and that is crucial. So back up here in question number 3, I clearly labeled it was molality, so that kilogram was just the water. This time, though, this liter is the solution, because molarity is moles of the solute over liters of the solution, which makes this a really interesting question, because we have to be able to solve this, to be able to do molality and percentage weight per weight, we have to figure out how much of the solvent we have. And there is. This is what I was looking for. This last piece of information down here is the key. So this is my assumption. And I'm going to start with my 1 liter of solution. And what I know, so I can change liters to milliliters, so 1,000 milliliters in a liter. And the solution has a density of 0.876 grams. So the nice thing, actually, I mean, even though you guys are in class, you can always go back and watch this again. You can stop it to catch up with my writing. And we would punch that in, and we'd get 876 grams. Now, again, back to the question that Aaron just asked, really important. Don't just ever leave a unit without a label. So grams is not enough. This is grams of the solution. All right, so the other thing we know is we have 0.21 moles of C7H8, and I'm going to label it extra just so you guys are clear. That's my solute. I have to change that to grams, and that's no problem. We can change moles to grams using our periodic table. And I did that earlier, which it's like 92.1 grams per mole. And we'll have to punch that in. All right. So 19 grams of the solute, which C7H8. I don't care which way you label it. I'll label it both ways, because half of you will do one and half the other. The question is an approximation, so I am only using 2 sig figs there. So my question for you, how much solvent do I have? Well, the solute plus the solvent gives you the total. So if we take the total and subtract the solute, so if we subtract, we'll get what, 857 grams? And that must be of the solvent, which is the C6H6. So now we can solve. And this is why you have to organize your work. Yeah, some of you aren't gonna, I think I give you plenty of space, but I know some of you won't think I give you enough space. And then also, just real quick, I had a typo on the worksheet, and so I reposted it at like 4 o'clock today, but it said somebody had already downloaded it. So if somebody's watching this and you printed the worksheet, you don't have to print it again. Just, it was like on the second page, I added explain your answer or something. But I don't know if it was any of you guys, or it may have even been me. Sometimes I look at it to see if I posted the right thing. All right, from there, I think you know how to solve it. So molality is, again, moles per kilogram. But if you get nothing else from this, you can't just say moles per kilogram. You have to say moles of the solute. And again, molality is the one that's the odd one. It is, the denominator is just the solvent. So yeah, so you can pull your pieces together. We know the moles of the solute right there, 0.21 moles. So that goes on top. And you can just keep saying solute or the C7H8, or you can write the word out, toluene, which actually is a really cool topic. Benzene's kind of a depressing topic. Benzene was the classic carcinogen that all the original carcinogenesis studies were done with. And then the solvent we know is 0.857 kilograms of just the C6H6. And then we punch it in and we get, maybe I should see if my answer's right. I'm assuming it's right. Yep. Oh, you know, this is the one everybody always asks me. I get right now that it's going to round. So 0.24, 0.25, I think it depends on how many sig figs you were using. And you can say moles per kilogram. We are limited to 2 sig figs because of that number there. So I just tried to respect sig figs throughout the problem. Percentage, I would change it to M per M. So that's going to be the grams of the C7H8 over the grams of the solution. So the 19 over the, we can write it out, the 19 grams over, which we figured out up here, over the whole 876 grams, sorry. And then times 100, so 19 divided by times 100, so 2.2%. All right. So 2 pages down, 1 to go. I'll leave that there for a minute while I see where I, all right, we're gonna go back over colligative properties unless somebody's got a question. Those of you at home can rewind if you have a question. So I'm gonna move that and we'll go to the last page. And those of you watching at home, 13 of you have topics now, which is really exciting, but we're going into the 8th week. When I see you again, it will be like only 2.5 weeks to go. So hopefully you all have a topic. You can email me topic ideas and I'll give you a thumbs up. All right, colligative properties are, again, when you add a solute, it changes the solvent properties. So solvent properties. So just to review, we went through these the other day. Vapor pressure is the gas that escaped the liquid. So the key here is that it escaped the IMFs. So the liquid has IMFs. And when you add solute, the solute and the solvent love each other. They have even higher IMFs. So if you increase the IMFs, you decrease the vapor pressure. Less escapes. So simple enough. So vapor pressure goes down. All right, freezing point. What happens to freezing point? As you add solute, it interferes. Remember, a solid, what makes a solid special is the pattern. So it interferes with the solid's lattice structure or pattern. So again, we see a decrease in the freezing point. Again, that's the freezing point depression. We usually do a lab with it. It's actually a pain in the ass lab, excuse my language, but the lab itself doesn't take so long. It takes like an hour, and then it takes an hour to do the cleanup because it's non-polar and it all becomes this fatty mess. It's like cleaning up bacon grease. All right, when you boiling point, because of the love, the higher IMFs, you need more jiggles or giggles or wiggles. So you need more of all of that. So you need more jiggles to overcome. And so you get a higher boiling point. And then osmotic pressure. The big picture is that one also goes up. So boiling point and osmotic pressure, boiling point and osmotic pressure rise when you add solute. Vapor pressure and freezing point decrease or depress. And the reason is that is, again, the solvent is attracted to the solute. Isn't this great? We can draw lots of hearts. So, yeah, and I really enjoyed everybody who did meditation. I really enjoyed reading people's experience. It was really inspirational. So thank you for that. So I know On loves the one that I do, which is sending love out to other people. It's really powerful. So if you haven't tried that one, I highly recommend it. It's only like 10 minutes long. And rather than just focusing on yourself, you end up focusing on other people. So osmotic pressure or osmosis, just a reminder, osmosis is the movement of the solvent. So this is all about the solvent. And so osmotic pressure would be the pressure to go against that. Reverse osmosis is when you can make the solvent move the other way. So the solvent always wants to go towards the side that has the solute because it's attracted to the solute. Reverse osmosis, so it would want to go to, so if you have water, fresh water and salt water, the water is attracted to the salt water because the solute's there. Reverse osmosis is when you're trying to pull the water out of the salt water. So it is actually extremely energetically demanding, except there's actually some really cool innovations with it. All right, the piece we didn't talk about the other day is this. So it's called the Bondt-Hoff factor. So that is spelled correctly, and it is the first Nobel Prize in chemistry. So the first Nobel Prize in physics was the X-ray guy, so Roentgen for X-rays. So the first ones were in 01. And so the first one in chemistry was this guy for electrolytes. And an electrolyte just means you have ions roaming aimlessly. So that's the picture there, and we're going to draw it a little bit better, because many years ago, another teacher complained that none of the students knew how to do that, but we'll just simply do sodium chloride. So when you put the sodium chloride in the water, of course, the sodium and chloride get pulled apart, but they keep their charges. So the sodium's a cation, right? Cats have paws. And the water molecule, the oxygen, is attracted to the sodium. Whoops, let me draw this further out. And it is the oxygen, because remember the oxygen has that partial negative. So we can draw another one up here. And I think that's what this picture is trying to show, but it got scrunched down too small. So if you had the water around the chloride, it would be the hydrogen that's attracted to the chloride. So in 223, we used to do a standardized exam, and I'm not sure how that can work if we're not in class in the summer. But this was actually a question on there, and it showed pictures, and maybe that would be a good question to have on your guys' midterm. So the hydrogen is positively oriented, right, the dipole, and so the positive part is attracted to the chloride. All right. Or any anion, any negatively charged. And so that allows them to move around, and so it conducts electricity. Because if you have charges moving around, it conducts electricity, and it does it really well. And this is the idea behind the lemon batteries or potato battery. Yeah. You can, apparently in Syria, when we were doing when they were bombing Syria and they had no electricity, people were charging their cell phones with lemons. So apparently, yeah. The hardest part about that is you need a whole bunch of alligator clips, because I think you need 4 lemons. But that's pretty cool. All right. I had a student in my class who was from Syria, and he was telling me the story. This was a couple of years ago. All right. So there is an assumption that we make. I'm going to do the problem at the bottom of the page, and then we'll come back up here. And the assumption we always make is if something is an ion, I did one like this the other day, that in water it splits into its ions. So the sodium chloride is not 0.5 molar, it's 0.5 sodium and 0.5 chloride. So it's really 1.0. And you can say 1.0 M. I actually often write it as osmoles. So because of the term osmosis, it was a term I saw somewhere. So you can either write it just with the M 1.0, or you can put the OS to say, okay, I factored in the number of ions. If we were doing calcium chloride, we'd multiply by 3. So the chloride's not a diatomic. You have a calcium ion and 2 chloride ions. So it actually breaks into all 3 ions. So we'd have the 0.6 times the 3 ions, and you would get 1.8 osmolality. So the OS just means osmosis is happening even more. All right, and then potassium nitrate. Just a reminder, NO3 is a polyatomic. So the NO3 does not get pulled apart. So you only have two ions here. You have potassium and you have nitrate. So you just have the two pieces. So you have 0.4 times 2 ions. So just be careful with the polyatomics. It doesn't break into potassium and nitrogen and oxygen. It just breaks into potassium and nitrate. And so this would be 0.8 osmoles. All right, so we have to go back to the beginning. Pure water. Does anybody remember what it was? Oh, there is no solute, so it's 0. Because to have a concentration, going back to our page back here, right, we always had our solute. So there's no solute. All right, so there's no solute, so it's 0. And then this one, it does not ionize, so it's considered, sorry, I'll write it like this, it's a non-electrolyte. So whatever number it is, it's still that same number. So we say 1 osmoles. So it stays the same. So it's not 0. 0 is if you truly had it deionized water, like in lab. Some of you have asked me in the past, what does it mean to be deionized? It means we've taken all those minerals, all those amazing minerals. It's not actually really good to drink pure water, deionized water, because your body needs those minerals. And so that's why if you actually have well water, you're really fortunate because you're getting the minerals from the ground. All right, and this then goes back to what we're doing up here. Which one has the lowest freezing point and the highest boiling point would be which one has the most solute. So our calcium chloride's our highest boiling point and our lowest freezing point. So the more solute you add, two things determine how much solute: the concentration and the number of ions. So you figure out the total together. And if I'd asked the opposite question, our 0 would have been the original, it's our lowest boiling point. So anything you add is going to raise the boiling point, and it's our highest freezing point. It was our starting point, the 100 degrees and the 0 degrees. And so everything either increased or decreased from there. All right. So we did one of those the other day. So my hope is with that, you guys will do pretty good. And then there's a comment Megan made to me, because the one worksheet, it was the gas law worksheet. She said, oh my gosh, this one was so much harder than the other ones. And I realized why. If you guys who had me last term remember the worksheets, they were always challenging. And I knew that this situation would be challenging for us because the communication would be limited. All the other worksheets have actually been quizzes that have been modified. So if you remember our quizzes, we always did practice. You've noticed there haven't been practice quizzes at the end of your notes. I don't know if anybody's noticed that. Those have become the worksheets. So with some modifications. So sometimes I'll bring in another problem. All right, let's do this problem up here and then we're good to go. This one brings in the von Hoff factor. So I made a huge assumption down here, and I fully ionized everything. It is a myth that your Chem 221 teachers taught all of you. Ions don't fully ionize. They almost fully ionize. So this I is telling you how much of it ionized. You will be given the I, or you're going to solve for the I. All right. So whenever you work with something that's an electrolyte, which just means it's ionic, so you have ions, you're going to either, if it doesn't give you a von Hoff factor, you just multiply by the number of ions like we did down here. But if I give it to you, we're going to use that number instead of the 2. All right, and I'm reading my problem. Yeah, and so usually I make ice cream for you guys in class. So make ice cream as a demo next term. I said in 223 you can do a demo. So a lot of you made bread for the gas law thing, so that you do making bread as a demo. All right. And you just have to explain your demos. So the demos are going to be a little bit more than what you guys did with the gas laws, because they're going to be worth more than 7 points. So we're doing freezing point. So since we're doing freezing point, we want to state our formula, delta T equals K times molality. So that was on page we did the other day. And so water freezes normally at 0 degrees Celsius. If water is not your solvent, I will tell you the freezing point. And then we put a lot of salt in there, and it now freezes at 10 degrees. So this is delta T is the change in temperature, so that would be 10 degrees Celsius. K is going to be given to you. It is different for every substance, and there is a K for boiling point and a different K for freezing point. So we'll just plug that in, the 1.86. It's funky units, so just go with the units. And I'm going to rewrite this M. That's simple. This is moles per kilogram. And so the moles are going to be on top, and the water, this is kilograms of solvent, right? So that's my water. We have 3.00000 kilograms of water. You can count your zeros. So we got to factor the I in somewhere. And the I always factors in wherever you had the moles of the solute is where you factor in the I. If there's an I, it goes with the moles of the solute. So I wanted to mention that because you can do it with molarity, you can do it with mole fraction, you can do it anywhere, it just goes with the moles of the solute. So this would say times 1.85, and the piece we don't know is this. So I'm just going to write this as X. And so now you have to rearrange and solve for X. And then I have to make a quick comment about positives and negatives. The 1.85 has no unit. It's just a number. Huh. All right, we must add a lot. So I got X is 8.7 moles. We're not done because the question wants to know the mass. So this is the moles of the sodium chloride, which I should have labeled up there. Back to the question that Aaron had asked me earlier, and I kept trying to emphasize, make sure you don't just say moles. Make sure you say moles of the solute or kilograms of the water. To get to grams, we would multiply by the mass, the molar mass from the periodic table of sodium chloride. So around 510 grams of sodium chloride, which is great. 2 sig figs. So the change in temperature is going to limit your sig figs. It is always just an estimation. And that is the biggest problem in lab is it was always just a hand waving. People would feel like they were off by 25%, and they would write these posts or their evaluation themselves and say, oh, I suck, I did awful in this lab, and it would be the 7th week and everybody would be dramatic. In this lab, that was actually good data. But a quick comment about positives and negatives. This is taught different in different books. So I've used 3 different books, and it's going to be different in different places online. I do absolute value. So I just consider the change in temperature always as a positive change. And I always make my K's as a positive K. Some books, this would be a negative change in temperature because you started at 0 and you ended at -10. So this would be -10, and they give the K as -1.86. So I just do everything as positive. Molality, molarity, concentration, the units that we were learning back here, these have to be positive. Moles are always positive. Grams are always positive. Volume is always positive. I is always positive. So I just keep everything as positive. Another thing is you will see the K as a capital K and the K as a small k. I learned it as a small k, so that's what I went with. But please don't let that confuse you or drive you crazy. That's just think of it as absolute value. That's such a small point and doesn't really matter. This has such a small niche use. The bigger point for colligative properties is this. The idea that why you add salt to water when you cook. Well, actually, why you add salt to water when you cook is usually so the noodles don't stick together and it gives it flavor. But when you add salt to water, you actually make the boiling point higher, which is fascinating. All right. Backside's blank. You can do whatever you want on the back. Do you guys have questions?
Ooh, I have one more.
Go ahead.
I was wondering if it's possible to have a negative OSM. Just curious.
I don't think so. How? Because you'd have to have that. So I'm going to say no for what we're doing. Is it possible to take something out of water that isn't there? That's like a question that gets into, well, that's a very esoteric question because we define everything as if the material world. So chemistry is really wonderful that I get to teach chemistry because I don't actually believe in any of this because this doesn't actually exist. None of us exist. This is all like a mirage, right? It's an illusion, but it's really cool because we can do math with it. Same with physics. Like all the laws of physics are wonderful, but it's all an illusion. But it can make us feel like we're smart. So the real answer to your question is absolutely. You can do anything you want to do. But in terms of this class, in terms of like, yeah, no. But that's why you can do anything you want because it's all an illusion. All right, any other questions? I'm going to hit stop record then. Figure out how.